We've reached week 5 now, so let's do a preview of the major topics of the week. We've labeled it space-time switches. There are actually a number of different topics we're covering, but the idea of space-time switches comes from the Lorentz Transformation, which we'll be talking about. It enables us to switch between different frames of reference very easily. But before that, we'll have the quotations of the week. We'll do that in a minute. We'll talk just briefly about convenient units for the speed of light, the concept of a light year, and the fact that if we measure distances in light years, a light year is a distance, the distance light travels in a year, as some of you may know. If we measure velocities in light years per year, then c, the speed of light, is simply 1. By definition, it's 1 light year per year. It's the distance it travels in 1 year. And so that, and a couple of tips there will make things a little easier for us calculationally when we do things. And then we're going to spend a little time looking at a case of time dilation and length contraction to build on the ideas we were working with last week. We introduced and derived last week to get some more familiarity with them, to struggle with them a little bit, try to get a deeper understanding of it. And we're calling this Star Tours Part 1. The idea is we're going to send, in this case, Bob will go on a trip to a nearby star, 5 light years away. The nearest star to Earth actually is about 4.2 light years away. We mentioned that in one of the early problem sets. But I think we mentioned in terms of the distance, not in light years, but just in how long light would take to get there. It's about 4.1, 4.2 years. Anyway, so we're just going to imagine Bob taking a trip there, and we're going to analyze it from Alice's perspective as she watches Bob take the trip to the nearby star, and she's on Earth. So we'll analyze it from her perspective and Bob's perspective. We'll try to make sense of both their perspectives, and then we'll sort of hit a wall, hit a puzzle, in that there'll be something that really doesn't make sense we'll get to. And so we'll have to hold that aside for a minute, and because we won't be able to answer it yet. And that's really what the next part here is. In order to answer it, we're going to derive the Lorentz Transformation. The Lorentz Transformation, just like the Galilean Transformation, allowed us to switch between different frames of reference in a non-relativistic manner. The Lorentz Transformation, also derived by Einstein, but typically called the Lorentz Transformation now, allows us to switch between different frames of reference when relativistic speeds are involved. And it actually is equivalent to the Galilean Transformation for slow speeds. So it subsumes the Galilean Transformation. So this will probably be the most algebra we do in the entire course. It will take us a while to get through it, several video lectures, but we'll work our way through it and then get these transformation equations. And then we'll spend a little time exploring those transformation equations, trying to understand them, seeing what they're telling us, see if they make sense from what we know so far. And then we're going to use those transformation equations. They're very general, useful in all kinds of ways, but we're going to use them to revisit this whole idea of leading clock's lag, because this will turn out to be the key to understanding our Star Tours conundrum that we end up with there. So we're going to revisit leading clock's lag and do it quantitatively. Find out exactly how much do leading clocks lag. Remember when you have a series of clocks moving by you, you're in one frame of reference, you see 2 or more clocks moving in another frame of reference past you, then the leading clock, as it's moving past you in that series of clocks, or 2 clocks, lags behind the rear clock. And we did that qualitatively before. Now we'd like to figure out exactly how much does it lag behind that clock, and that's going to be the key, as we discover, to figure out this problem we run into. So that's Star Tours Part 2 here. And then we'll say a few words about the ultimate speed limit, speed of light being an ultimate speed limit, and why that might be so, what would happen if you could travel at the speed of light. And then finally, talk about combining velocities. We did a little bit of this with sort of the Galilean Transformation idea, where if you have a car and you have a basketball shooting machine that we talked about, and then a tennis ball out of the basketball, that type of thing. In our everyday experience, those types of things just add. You add the velocities, or if the velocities are opposite to each other, you subtract the velocities. Well, a similar idea in terms of the special theory of relativity, but it's a little more complicated. Because if the speed of light is an ultimate speed limit, what if you have something traveling at 0.9 c, say Bob on his spaceship traveling at 0.9 c, and then he shoots out maybe an escape pod or something, traveling at 0.5 c away from him. So he's traveling at 0.9 c, 9/10 the speed of light. He shoots out an escape pod at 0.5 c, so that's 0.5 c with respect to him traveling away. In sort of classical physics, we'd say, oh, you just add the velocities. It's 0.9 c plus 0.5 c. Alice watching it over here as Bob goes by and shoots off the escape pod. Alice would say, presumably, 0.9 c plus 0.5 c, 1.4 c is the velocity of the escape pod as she sees it. But in actual fact, you will never see anything go past the speed of light. And so combining velocities here will show us the new formula for doing that, such that no matter how fast Bob shoots out that space pod or whatever, Alice will never see it go faster than the speed of light. Actually, will never get up to the speed of light, but it will never exceed the speed of light there. Okay, so that's sort of a rundown of where we're heading this week. Let's do the quotations of the week. 2 short ones this time. First one, Einstein. It's not that I'm so smart, it's just that I stay with problems longer. It's not that I'm so smart, it's just that I stay with problems longer. Now, I said Einstein, quotation from Einstein. In actual fact, Einstein probably did not say this. It's one of those things that somebody invented at some point, and it sounds good. It sounds like Einstein could have said it. It's certainly inspirational, and therefore you see it all over the place. In actual fact, it's something he could have said, because he certainly did stay with problems longer. He certainly was very, very smart. Hard to measure those types of things at a certain level, but great scientists also have this tenacity about them, and he was tenacious when he got onto a problem. We saw that in the special theory of relativity. It was about 10 years of thinking about that, other things as well, but 10 years from about 1995, 1996, when he started in the university, to year 1905, I should have said 1896 if I said 1996, to 1905, 10 years. And then actually the next 10 years after that, he spent a large part of time working on his general theory of relativity. It took about 10 years to work on that, as well as a number of other things as well. So that tenacity, that idea that I'm going to stay with this problem. Now, it's not always a benefit, because if you go off in the wrong direction, you may be going off in the wrong direction for a long time. And in fact, many physicists who are contemporaries of Einstein during the second half of his life felt that he had gone off in the wrong direction in terms of the physics of the day, which had gone in much more quantum mechanical direction. And Einstein had some real problems with that. And so really for the last half of his life, from about 1925 on or so, he was out of the mainstream of physics. He's certainly revered by many people and physicists, but just did not really contribute anything major at the time from about 1925 to he died in the 1950s. So again, it's a good quality to have, no matter how smart you are, however you want to measure that, but that just staying with the problem longer, that struggle for understanding we've talked about before. So even though Einstein probably didn't say it, it certainly captures one aspect of his scientific personality. And the second quotation, similar to the first, and this one is something he said, one should not pursue goals that are easily achieved. One must develop an instinct for what one can just barely achieve through one's greatest efforts. And so there's that insight into you want to tackle problems that are challenging for you, but you also have to have some insight sometimes, is this just too hard a problem? And scientists have to have that as well. They have to understand, given our current capabilities, our current understanding, my current abilities maybe, that's just something, it's not good for me to tackle. Leave it to somebody else, or leave it for 20 years from now, and maybe we'll be able to come back and tackle that problem again. On the other hand, sometimes the really hard problems like that, the only way you really do crack those nuts, as it were, is for somebody to take it on, or a group of people really to take it on and to stay with that problem until it gets solved. Okay, so that's overview of the week, where we're heading, quotations of the week, and again, we're going to be building on the things we've been doing the last couple weeks now with the key concepts of the special theory of relativity and seeing what some of those implications are for our situations, not only with traveling to stars maybe, but also combining velocities and ultimate speed limits and the like.